In this video, I'd like to perform the first derivative test to talk about a change in increasing and decreasing behavior. So I've got this function, I'm going to call that omega x. It's x to the 2/3 power times 2 minus x. And I want to know, basically I want to perform the first derivative test. So before I do that, I need to always mention the domain. Now the domain of a cube root function is not restricted. It goes all the way left and right. This piece is linear, so I'm not going to have any sort of domain problems. If I were curve sketching, I would then probably go off and find vertical asymptotes, there are none, and then horizontal asymptotes, which may be a little bit more difficult. But I'm going to jump straight into the first derivative test. I'm going to find omega prime, the first derivative of omega. I could rewrite this, but it's written as a product, so I'm going to go ahead and apply a product rule for differentiation. First, d second plus second d first. I'm going to clean that up some. Well, that's a negative. And then, looks like I'm going to have a fraction. The 2 minus x and the 2 will stay in the numerator position. I have a 3 in the denominator, and I'm going to kick this x down to the denominator to call that a positive 1/3. Now, if I want to simplify further, I should get a common denominator. Easy. I can multiply the first term top and bottom by the common denominator, 3x to the 1/3 power. When you find a common denominator, you're just multiplying by a fancy 1, so you're not changing any values. So I have negative 3x, and when you multiply common bases, you just add the exponents. 2/3 and a third will be 3/3, which is 1. Fancy. Nothing changed here. I can see though, now that I have an x to the first power, if I distribute my 2, I'll be able to combine like terms. So I'm going to go ahead and multiply that 2 out. I have a common denominator. I'm going to go ahead and add. So the x's join up to be -5. So I have 4 minus 5x over 3 times, and you may want to convert this back into a cube root if you want to, that's fine, cube root of x. So omega prime, the first derivative is 4 minus 5x over 3 times the cube root of x. That's the first derivative. Now the first derivative test is to go off and find critical values. Critical values occur 2 ways. One, any new domain restrictions. Oh my goodness, I think we have one. Originally, my domain was not a problem. Now, though, there's a number I cannot divide by, right? There's a number I can't plug into this cubed root. If I plug in 0 into the cubed root of 0 is 0. 0 times 3 is 0. I cannot divide by 0. So I have a domain restriction. That means I've got a critical value at 0. Okay, critical values also occur from the roots of the first derivative. So that just means I need to set this equation equal to 0 and figure out its roots. Now this is extremely convenient here. I'm about to multiply both sides of the equation by 3 times the cube root of x, and that 0 is just going to swallow it up. Gone. 0 equals 4 minus 5x. This is easy to solve, nice little linear thing. Kick over the 5x to make it positive, divide the 5, make it a positive 4/5. We have a critical value when x is 4/5. What do I do with these critical values? Oh yeah, I put them on a number line summary. And I put them in order, so 0 comes first, and then 4/5. And then what do? I want to test the first derivative. So I'd like to know basically a value less than 0. I'll try something easy like -1. Between 0 and 4/5. 4/5 is shy of 1. I don't know, a fifth? If I were smart, I'd look back at what I'm going to have to test. A fifth would be nice, because that's easy to multiply. It's not easy to cube root, but I think I'm going to choose 1/5. And then I need a number beyond 4/5, so I'll just choose 1. These are numbers I'm going to test my first derivative. In fact, I'll just use a different sheet of paper for that part. So when I plug in -1 into my first derivative, I get something like this. 4 minus 5 times that -1 over 3 times the cube root of -1. And remember, when we're finding critical values, all I'm really concerned with right now is the fact if it's positive or negative. Let's go. 4 plus 5 is 9. The cube root of -1 is still -1. 3 times -1 is -3. So I get -3 in the end. What I really care about, though, is the fact that this thing is negative. Because where your first derivative is negative, the original function, w, the one that I'm trying to talk about, the one I'm maybe trying to sketch, it will be decreasing. I now know that this function, the original function, starts off probably at infinity and is decreasing until I get to the critical value of 0. Now there may be a change in behavior at 0. So now I need to test what happens between 0 and 4/5. Same process. Go to the first derivative, plug in not 0, plug in the test value, 1/5. Now I don't know the cubed root of 1/5, but I don't care because all I care about is if it's positive or negative. In fact, I'm just going to put a plus sign down here. I know the cubed root of a positive number will remain positive. Up top, I can do this real easily, except, did I do that right? Yeah. 5 times a fifth will be 1. 4 minus 1 is 3, which is a positive number. So this is going to be positive in the end. I'm going to go back to my number line summary, and I'm going to say, hey, here I am positive, meaning my original function is increasing. On that interval, 0 to 4/5, I am for sure increasing. So I started off decreasing, I got to 0 on the x-axis, and I turn around. Let's try a number beyond 4/5. Let's try positive 1. Well, the cubed root of 1 is still 1, so down here I've got 3. A positive is what I'm really after. 4 minus 5 is a negative 1. Now here, I'm going to be getting out a negative result. So I'm going to have a negative at the first derivative, which means my original function is decreasing. So I did change behavior at both of my critical values. If I wanted to sketch this function out, I know I'm decreasing until I get to 0. I then start to increase until I get to 4/5, and then I start to decrease forever. Intervals of increasing, decreasing behavior. I could say I'm increasing along the interval 0 to 4/5. I'm decreasing along the interval negative infinity up to 0, union that with the interval 4/5 to positive infinity. If I want to go off and find the maximums, this local minimum and this local maximum, because it's the high point in this area, the low point in this area, I can plug in these values back into the original function. The original function tells me xy coordinates. I'll have a local min when x equals 0. So I'm going back to the original function and plugging a 0 into omega. Oh, well, that's just going to be 0. 0, the cube root is 0, 0, 0 squared is 0, 0 times that is 0. So the origin is a local min. The local max, now I'm going to plug in the other critical value, 4/5. Oh dear, I don't want to do that anymore. I don't want to do that. I want to switch over to technology. In fact, let's just take a look at this picture just to confirm what we are looking at. So, right here, I see the function omega, and yeah, if I start off from positive infinity, moving left to right, I'm decreasing down until I get to the origin, 0, 0. I seem to have like a kink or something, and I come back up, and I do have change behavior. I go from increasing to decreasing there at 4/5, and then I start to plummet down. So there we go. I like it. All right, so there's the first derivative test. Hope that helped. See you next time.